Measurement system analysis or measurement system capability analysis. It is also known as gauge R&R study or gauge repeatability and reproducibility study. We'll discuss about how to perform that using Microsoft Excel in this video. So all you need is basically a simple Microsoft Excel, and this is a based on the range method or control chart method. So we're going to first create the control chart, and then there are some additional calculation for the repeatability and reproducibility part. So first we need some equations. For example, this revised control chart equation. We'll hope that, well, we'll assume that the data is already clean and nice. Now, to find this equation, you can go to the openeducator.com, and then under statistical quality, the first link is the equation file. So you can get all those equation from there. So to start with, we need to calculate first the X bar for each of these measurements of this part, the average of these three measurements, and then we need to calculate the grand mean, which is X bar bar. So grand mean is basically the average of all the data points, like that. And then range, there is no Excel function for range, so we're going to do max minus mean. So maximum of these three measurements minus the minimum of these three measurements, that will give us the range. And then we also need range average. So range bar, simply we can average this column, that will give us the range average. Then the upper control limit, lower control limit, upper spec limit, lower spec limit. Let me copy this down. So we have that. Now let's calculate the control limit. Now to calculate the control limit, we need the constant value. So the formula is X bar minus plus A2 sigma 0. So A, constant A, you can also find that constant table in the openeducator.com. Let me find that constant table. Control chart constant. So here is this for three measurements. Value for A is 1.732. So 1.732, and D2 value is small d2 is, let me see that. So a small d2 is 1.693. 1.693. Then we can calculate the sigma 0, which is the range divided by d2. And then the upper control is basically the X bar bar plus A times sigma 0. And I should freeze both of them because I'm going to use them again and again for all 20 parts, like that. So lower control will be simply the negative sign. Also, this has been moved one cell more. So then just copy all the way down, like that. Upper spec, lower spec will be typically given. Let's assume 65 and maybe 5. Something like that. It will be given in the question or in the problem. It comes from the customer typically. It could be internal or external customer. So we have just produced this control chart. Let's see how they look. So insert control chart like that. As you can see, let me delete this spec limit first so that we can see the chart a little bit wider and explain a little bit better. So here you can see that these points are out of control. They are very crazy type of situation, which is in fact good. because this control line is based on, as you have seen here, the formula. Let me go to the formula here. So that is the x bar plus a times sigma 0. This sigma 0 is the gauge standard deviation, so the variability due to the gauge. So if this value is low, then you are adding with this sigma x bar, you are adding very low and subtracting very low. So the control limit will be very narrow. So narrow control limit, all the points are out of control, which tells us that this is a good measurement system. Now let's calculate some more parameters so we can see how good is this measurement system is. So one of the things that is calculated is called the gauge capability, which is precision to tolerance ratio. So that is 6 sigma divided by this upper spec minus lower spec. So that's 6 times sigma, which is this, divided by the upper spec minus the lower spec. So that's the gauge capability, which is 0.06. So anything less than 0.1 is considered a good measurement system. So anything less than 0.01 is considered adequate measurement system. So it's a good measurement system. Anything over 5 is considered bad. So we can write that here too. So anything over 0.5, anything over 0.5 is considered a very bad measurement system or poor measurement system. So that's one parameter. We have a couple of things more. One is we can see the ratio of the gauge variability, because this is the gauge standard deviation. So then the variability would be basically square of that. So this times this will be the variability of the gauge. Now the total variability or total standard deviation can be calculated using, simply you can type a function called stdev.s and then select all these measurements. So that will give us the total standard deviation. So then the total variability that includes the process variability, also the gauge variability, the measurement system variability. So that is basically equal to this times this, again is square of that. So the percent variation due to the gauge or the measurement system is basically the gauge variability divided by the total variability times 100. So as you can see here, only 0.91% variation is due to the measurement system, so which is good, and then everything else is due to the process. So basically 100 minus this is about 99% is due to the process variation. So to summarize, first you create the control chart and you see if the points going out of control, that indicates that the variability is very low, that making this control line narrower, and that indicates it's a good measurement system. You have a very low variability for the measurement system. The deviation is low for the measurement system compared to the process or the part that you're measuring. And then next we calculate the precision to tolerance ratio, which is the 6 sigma gauge sigma divided by the upper control, lower control. You can see the formula here, also in the openeducator.com. And if it's less than 0.1, then it's a good measurement system. Anything over 0.5 is considered bad. And then of course you can calculate the percent of variation due to gauge and then percent of variation due to process. So we'd like to see more variation due to process than our measuring system, and that tells us the measuring system is good.